Hello everyone. In this lecture, I focus on linear programming models. So far, we discussed predictive models which refer to knowledge discovery techniques. We had some historical data sets and we used them to train our algorithms, and we wanted to know what will happen in the future. All regression models, neural network, and clustering algorithms go under this category. There is another modeling approach named prescriptive models, which recommend a course of action to a decision maker. So we want to answer this question: what should we do to achieve our goal? All mathematical programming models, including linear, integer, stochastic, and network flow models, go under this category. In particular, in this lecture, I will be discussing the elements of mathematical programming, the steps required for linear programming formulation, data requirements for an LP model, and how we can use lists and dictionaries to summarize the data, and briefly discuss linear programming solutions. There are three main elements for mathematical programming. The first element is decision variables, the inputs that the decision maker can control. In order to identify decision variables, we need to answer this question: what are the inputs that can be controlled? For instance, how many items do we need to produce per week? 10 items, 100 items, or 1,000 items? So that's the decision that we can make. The second element is constraints, which refer to restrictions on the decision variable or potential solutions. In order to identify constraint, we need to answer this question: what are the rules to which any solution must conform? For instance, we always have budget limit, so we want our solutions to be within that limit. The third element is the objective function, which is a mechanism for scoring or rating solutions that satisfy all of the constraints. We might have several solutions which meet all the constraints that we just defined. Now, what is the scoring measure we use to compare alternative solutions? Because eventually we want to choose the best solution. And that's why we say prescriptive models recommend a course of action. Linear programming models are planning problems where all of the mathematical functions in the problem are expressed as linear functions of the decision variables. In this course, we only focus on LP models. Now, let's go over the assumptions of linear programming models. The very first one is linearity. It means that the value of the objective function and the response of each resource expressed by the constraint is proportional to the level of each activity expressed in the variables. It also means that the effects of the value of each variable on the values of the objective function and the constraints are additive. Means that we don't see any interaction terms. We don't see x1 times x2. They're all additive. The second assumption is certainty. It means that all parameters, including coefficients and constants, are assumed to have known values. The cost for producing one item is $10 or $20. We know this value and it remains the same. Divisibility. Decision variables can have fractional values. So they can take on 2.2 or 2.3, for instance. And the last assumption is one objective function. So we deal with a single criterion problem in order to rank our solution. There are three main steps for formulating a linear programming model. As you can imagine, the first step is to define the decision variables and their unit. Is it time? Is it dollar? And the next step would be expressing the objective function in terms of the decision variables. So if you are not able to express that function in terms of decision variable, we go back and look at our decision variables again or redefine them. And the third step is to express the set of constraints in terms of the decision variables. And if we are not able to find those constraints, we go to step 1 again. There are two types of constraints. One is a structural or technological constraint, like budget limit, or the case that we only have 2 people who can work only 8 hours per day. The other type of constraint is non-negativity constraints for decision variables. For instance, decision variables should be equal or greater than 0. We should note that both types of constraint should be included in a formulation and when we want to solve it in Python. So both should be included. Now let's briefly talk about data requirement input parameters for an LP model. You can see a table in this slide which has several columns and several rows. The columns activity 1 and activity 2 refer to decision variables, so we can change those values. And each row refers to the resources available for producing those activities. If you focus on column activity 1, in order to fill in the table, we want to know that how many units of first resource is required to produce activity 1. How many units of second resource is required to produce activity 1. And that's how we fill in the table. The same process for the second activity. And the last column is the threshold. So available resource. It means that resource 1 is available equal or less than this number. So if that resource is available for 10 hours, then we cannot assign more activities which require more than 10 hours. It's just not feasible. You can also see the very last column, which shows the contribution of each, the very last row, which shows the contribution of each activity to the objective function. It means that if we increase activity 1 by 1 unit, then the objective function will be increased by C1. The same for the second activity. So if we want to write the objective function in terms of decision variables, then it's pretty straightforward here. So the objective function z is equal to C1 times activity 1 plus C2 times activity 2, and etc. So that's additive and proportional. If we increase activity 1 by 1 unit, and the objective function increases by this coefficient. Now I would like to discuss an example to see how we can go through these steps in order to formulate an LP model. Let's say the window glass company makes glass windows and doors. So there are 2 types of products here. The company has 3 plants. P1 makes aluminum frames, P2 makes wood frames, and P3 makes glass and assembles finished product. So it means that these are the resources available for the company. 3 plants. The plants are restricted by the available labor hours per week. So this is the restriction, the constraint. And the unit is labor hours per week. The goal is to maximize the profit. So now we have the objective function. It's about maximizing the profit. So when we sell 1 batch of windows, then it produces profit. So the question is, how many items do we need to produce in order to maximize this profit? Now here is more information. Each batch of doors requires 1 hour at plant 1, 0 hour at plant 2, 3 hours at plant 3. And each batch of windows requires 0 hours at plant 1, 2 hours at plant 2, and 2 hours at plant 3. We also have the profit information. Profit is 3,000 per batch of doors. So if we produce one batch, then we make $3,000. Profit is $5,000 per batch of windows. Okay, so these are the input parameters or data that we have. Now, weekly available labor hours are as follows. We only have 4 hours available at plant 1, 12 hours available at plant 2, and 18 hours at plant 3. Now let's see how we can summarize this information in a table. In our table, the columns represent decision variables or activities. In this example, we have 2 types of activities, producing doors and windows. And each row represents resource. So here we have 3 plants, so we have 3 resources. In order to produce one batch of doors, we need 1 hour at plant 1, 0 hour at plant 2, and 3 hours at plant 3. And this is coming from this information, 103. The same for the other column. In order to produce one batch of windows, we need 0 hours at plant 1, 2 hours at plant 2, and 2 hours at plant 3. And each plant is available 4 hours for a limited hour per week. So plant 1 is available only 4 hours, plant 2 only for 12 hours per week, and plant 3 available for 18 hours. And that's how we fill in the table. And we can now use lists and dictionaries to save this information. So we can define a list for products, doors, and windows. We can define another list for resources, P1 through P3, because list is a sequence of items. We can also define a dictionary for each pair of product and resource. So the key becomes the pair of each row and column, and then the values are in the table. So P1 doors, the value is 1. P1 windows, the value is 0. I would like to refer you to lecture 5 that would discuss how we can extract several pieces of information from a table and use lists and dictionaries as data structures to save this the information. The example we discussed in lecture 5 is very similar to this one. Now that we have defined decision variables, we know the resources, then we can use mathematical formulation. So we can define our objective function, which is to maximize the profit, 3,000 times x1 plus 5,000 times x2. So I dropped $1,000. So if we produce one batch of doors, then we have 3,000. And if we produce one batch of windows, then we have $5,000. Then in order to write the constraint, we can look at the table that we have here. So there is a constraint for each available resource. So 1 times x1 should be less than 4. So this column is the right-hand side in your equation, 4, 12, and 18. And the coefficients are the values that we have in the table. We also have non-negativity constraints. Both decision variables should be equal to 0 or positive. They cannot be negative. Now, we want to find the best solution. What is the best combination of products that we can produce in order to maximize the profit such that we meet this requirements? So if we solve it, we realize that the best solution is to produce 2 batches of doors and 6 batches of windows. And in that case, we make $36,000. Here you can see the generalized formulation. So the objective function is the summation of coefficients times decision variables, and the set of constraints is the summation of coefficient times decision variable less than the limit, the threshold. So this is just a generalized formulation for LP models. Now, for sure we are using one of the libraries in Python to solve the model. But what kind of solutions do we expect? Here we can see three types of solutions: feasible solutions, infeasible solutions, and optimal solution. Feasible solution means that refer to solutions for which all constraints are satisfied and might not exist for a given problem. So for some problems, we just don't have feasible solution. The way that the constraints are defined make it impossible to have feasible solutions. We can also have infeasible solution, just like what I discussed right now. So solutions for which at least one constraint is violated. It's just infeasible to find some solutions, or at least one, which meets all constraints at the same time. And the other one which we are more interested in is optimal solutions. It means that it has more favorable value of objective function. And again, might not exist for a given problem. So it's possible that when we solve a model in Python and we don't get any optimal solutions. But once we get the optimal solution, it means that this is the best solution. There is no other way to improve our objective function. So in the next lecture, I will discuss implementation, how we can solve LP models using GrobyPy library.